Good afternoon, everyone. Thank you for joining in for the post-lunch session on the final day of this conference. In this session, we have 7 paper presentations. Each paper will have roughly 20 to 25 minutes for presentation, and then the chairs will ask questions for roughly 5 minutes. I request the chairs to kindly read out the paper titles and invite the authors to present their papers. So the 3 chairs for this session are Dr. Joydeep Sengupta from VNIT, Dr. Anurag Hamilton from UEM Jaipur, and Dr. Shahadev Roy of NIT AP. Now, I request the chairs to please take the session forward and invite the speakers.
Hello. Good evening,
Yes,
everyone.
yes, Dr. Sengupta, you're audible.
Okay.
Just a small announcement. Someone has joined the meeting with the name T. I request that participant to write his or her full name. Without writing the full name, we'll have to remove that person. Please, anyone joining the meeting, write your full name. Thank you, sir. Dr. Sengupta, please, you can continue.
Okay. So, the serial number 1, paper ID is 110, optimal path planning with smart energy management technique using Dijkstra algorithm. The authors are Subhajit Bhattacharya and Mousumi Karmakar. So I am requesting you to present your slides.
Am I audible, sir?
Yes.
1 minute. Hello. Hello. Am I audible, sir?
Yes, you are.
Is my screen visible?
Yes, it is visible.
Okay. So my paper ID is 110 and myself Subhajit Bhattacharya and my co-author is Dr. Mousumi Karmakar. We are both from Mallabham Institute of Technology from the ECE department. And the title of our paper is Optimal Path Planning with Smart Energy Management Technique using the Dijkstra algorithm. Now, one minute. Okay, so the outline of the paper is arranged as follows. First is the introduction of the paper. Next, we will discuss the classical Dijkstra algorithm. And third one is the proposed methodology. That means whatever work we have done in this paper that will be discussed in this section. And fourth one is the mathematical calculation that is needed in this paper to calculate some of the vital point regarding this paper parameter. And last is the result and discussion, and the conclusion and the future one. These are the outline of our papers. Next is the introduction. So before the introduction, I would like to say that our paper, main motivation of our paper is to minimize the energy while transportation and traveling. Now in the nowadays, transportation and the traveling both are required in variety of business. Variety of business means someone is likely to see their near and dear ones, so someone has to travel between 2 points, or the other business companies and the houses of the different MNC companies, they will need the logistics and the transportation to transport their product to the intended customer. So that's why transportation and traveling from the inception of our society, earth, that is, these two things are very much necessary. And here we will try to introduce these two concepts and try to minimize the energy criteria for the while traveling or transporting something between the two places, because energy is the most vital or the costly thing in today. So we will try to model the energy or try to minimize the energy in this paper. So next, to model the efficient transportation of the traveling problem, here we use the shortest path algorithm. Now the Dijkstra algorithm is very much popular algorithm in context of the calculation of the shortest path while in a graph structure of the tree structure. Whenever we try to model a particular portion of a road or a section, then we can model it, use it the different vertices and the edges connecting between the points. And whenever we try to move the between two vertices, the Dijkstra algorithm gives us the shortest path between these 2 points. But here we will not use the shortest path concept emphasizes in this paper. We will emphasize in this paper that the minimum cost is required. But most of the paper before our work is actually concentrating on calculating the shortest path between the 2 points. Now coming back to Dijkstra algorithm, it is a greedy approach. Okay, that means this algorithm use the greedy approach to find the shortest path from a given source to the destination in the vertices. That means in the graph there are edges and there are vertices, and we are trying to calculate the shortest path between any two vertices. Dijkstra algorithm is efficiently gives us the shortest path between the two vertices and gives us the distance in terms of kilometer or meter, whatever may be. But here we don't use the A-star algorithm. A-star algorithm is also a algorithm which can use to give us the shortest path between the 2 points. But apart from the actual cost, A-star's algorithm also use the heuristic distance between the 2 points. So heuristic distance calculation is very much difficult, and if the heuristic distance is not accurate, we did not get any accurate result. That's why we are eliminating the A-star algorithm. And we here did not consider the negative edge cost. That's why we did not use the Bell-Manford algorithm, because Bell-Manford algorithm is used to calculate the shortest path between the 2 points when negative edge cost is considered. But here in our work, we did not consider the negative edge cost between the 2 points. That's why we did not calculating or use the Bell-Manford algorithm. So our motivation or for the paper is this. Now our aim of this paper is the proper path planning between the 2 points using the smart energy management technique. Now the smart energy management techniques means we want to not only we are interested to find the shortest path between the 2 points, we are also interested in minimize or emphasizes the fact that we want to minimize the energy consumption while traveling between the 2 points. So that is our motto or the aim of the paper. So that's why we improve the efficiency or the energy efficiency while traveling between the 2 points for better utilization of the available resources. So that is our motivation from 1 to 4 point, and our aim of the paper is the last point. Next, the classical Dijkstra algorithm. Now we have represented 3 slides regarding the classical Dijkstra algorithm. First, we will outline the different steps while calculating the shortest path between the 2 points. That is the written here. Next, we will give the pseudo code, and next in the third slide we will discuss the animation video so that everyone can get a view how the shortest path or the calculating the shortest path is used using the Dijkstra algorithm. Now I think from the third slide onwards it will be very much clear to everyone. Now in context of the classical Dijkstra algorithm, there is a graph, and in the graph structure there is a vertices, and the 2 vertices can be connected through an edge. So that is all about the graph structure. Now we have considered a graph structure, and from that point, starting point, all the distances is set to 0. Okay, but all other point and distance to infinity. That means starting point distance is set to 0, and all other point distance from the source had been set to infinite. That is the first point. Second point is, whenever we created the non-visited node for all points, including the starting point, that means we have created an array or the stack, anything you can create that will give track record of all the non-visited nodes. Okay. Second, the third point is, in the subsequent steps of the algorithm, that means our aim of this in the Dijkstra algorithm to reduce the cost between the two paths that we are going to calculate from the third points onwards. Now, whenever the new cost of the unvisited node, that means the 2 points, and the current node is calculated, and if the current cost is less than the sum of the previous cost, then we will update the new cost, otherwise we will retain the previous cost. So in this way, we are going to give a loop until the minimum cost between the source nodes to the destination node is calculated. So that is the outline of the classical Dijkstra algorithm. Now this is the pseudo code. Now the pseudo code is, as I have said in this slide, that the starting point distance is set to 0, all other point distance is set to infinite. That is been written down here, that the distance in the source is source distance is given to 0 at the first point, distance to source is 0, and all other point distance from the source is set to infinite. So that is given here, distance ends set to infinite. Next, we have created a empty visited node. That means the apart from the source node, we have give track of all other node that has not been visited yet. Okay, so that is the empty node in the S, and Q is contain the initially all nodes. So S is the empty node and Q is the all node in the graph. Now, while Q is not empty, until and unless we have visited all the nodes, then we will give a loop. So that loop is nothing but you calculate the between the 2 point distance, and you will give track of this distance, and otherwise the new distance is less than this distance, we will maintain this distance if the neighboring through other nodes, that means the distance n greater than distance u plus n. That means these two line actually represented that between the 2 points we are first getting a distance, and if it is written throughout our loop, that means if no other distance is less than this distance, we will retain this distance, otherwise we will update the new distance with this distance. So that is the pseudo code for the Dijkstra algorithm, and we have implemented this code in the C++ language. Next, this is the animation. This animation is very much good, and I think all of the algorithm that I have discussed, the pseudo code and the steps, that will be clear to you. So I am just running this video. This is a small video. Now, in this video, 1 minute, the video will start. So in this video, you can see that first, this is your 0 node, source node. It has been set to 0, and all other nodes distance is set to infinite. Now you process the 0 node and calculate the node 1 distance that has been set to 4. Next, we will go to node 0 to node 2. That distance is set to 3, less than infinite. So we will update this as 3. And in this way, we will again go to the other node. That means node 0 is being done here. Next, we will go to the node 1 from this node. From this node to that node's distance is calculated, and it has been updated. And it has been updated throughout this. Okay. So from 0 to 4, it has been 6. So that's why it has been updated. Less than infinite, 6. After that, it will go on. From 1 to 3, it has been 7, less than infinite. So it has been again updated. Now node 1 has been done. Then we process the second node. So second node to third node distance is 6, which has been from 0, 1, 3, it has been less. So that's why we are updated through the node 2. So node 2 is done, no other node is connected. So then we try to process the fourth node, and from the fourth node onwards, we will calculate the distance of 3, which has been 8. So 8 is greater than 6, so we will retain the previous distance. And from the fourth node, again, this is the destination node, which is 12, less than infinite. So we will update first this distance 12, and we will try to calculate from this node 3. From the node 3, it has been processed, and the distance calculated is 7. So 7 is less than the previous distance, so we will update it 7. So in this way, we are calculating the distance. So all of the node has been done. So in this way, we are calculating the distance from the source node to the destination node. So that's why distance has been updated as 7. So that is all about the Dijkstra algorithm. The source node has been set to 0, all other nodes set to infinite. And in this way, this algorithm runs in a loop. Otherwise, the destination node is reached and all other nodes that has been marked red has been visited. So this is the all about the Dijkstra algorithm. Here is the vertices is 0, 1, 2 like that, and edge is 0 to 2, distance is 4. So that is the edge between the vertices 0 and the vertices 2. So our proposed methodology. So in the previous slide, we have seen that we have calculated the shortest distance. Okay, now it has been found that all the time our energy is now the important than the distance. That means the distance between the 2 points may be less, but sometimes it has been found that due to different condition. Now different condition between the 2 points, the energy consumption between the 2 points may be higher. So that's why we will not concentrate between the shortest distance between the 2 points. Rather, we will try to look into the matter of the energy, because energy is very much valuable. So that's why we will try to calculate the energy consumption between the 2 points, which is minimum, not the shortest distance. So shortest distance we are not calculating. So we are replacing the distance between the 2 vertices with the energy consumption, and based on the use of the Dijkstra algorithm, we will try to calculate the energy consumption, not the minimum path. We are trying to calculate the energy, minimum energy consumption between the 2 vertices. Method is same, but here you need to calculate the energy consumption between the 2 points with some sort of mathematical model. So the mathematical model is, and this is our proposed graph. Okay, this is our proposed graph structure. That means node 1 to node 6. And here you can see that between the node 1 and node 2, distance is 3 kilometers, but the energy consumption is 5 kilowatt hour. And that has been represented in this graph. Okay, that means the source node is 1, destination node is 2, energy consumption is 5, distance is 3, like this. Like this, node 3 and node 4. Between the node 3 and node 4, the energy consumption is 10 kilowatt, but the distance is 7. So in this way, we have calculated all the energy consumption between the 2 points with the help of distance calculation is very much simple, but the energy consumption is somehow difficult. We have used a paper, a reference paper, which has been cited to how to calculate the energy consumption between the 2 points. And we have used this formula and calculate the energy between the 2 points. So that is our model. Okay. So next, this is the mathematical calculation. Mathematical calculation is actually associated with the energy calculation between the 2 points. So how the energy is being calculated between the 2 points. So that has been proposed here. And here you can see that the total energy consumption is composed of, this is the inertia force, and all have been written down here. This FRR, this force is due to the friction. FGRA, this force is due to the gravitational force, and FD, this is the aerodynamic force. So all of this equation has been written here, and we have calculated. We have also know the each of the coefficient value. Okay, and from there we have calculated the energy consumption between all the vertices in the graph. Okay, and this is the meaning of the different coefficient written down here. That means CD. CD is for the drag coefficient like this. AF is for the frontal area, vehicle mass, gravitational force, rolling coefficient, like this. Okay. So in this way, we are calculating the total energy between the 2 points, calculation of total energy, which is totally independent of the distance between the 2 points. That means the distance between the 2 points is nowhere connected to the energy consumption between the 2 points. That is very much related here. Now the result and discussion. Now in the result and discussion, what we are calculating, I have already mentioned that the original Dijkstra algorithm trying to find out the shortest path between the 2 points. And here we are calculating the energy consumption between the 2 points, considering all other the root parameter, and that energy is being replaced between the 2 vertices. And from that, with the help of Dijkstra algorithm, we are trying to find out the shortest energy consumption between the source and the destination. Now energy consumption can be varied due to the different factor. That means the energy efficient route, that means the road condition, traffic congestion, road gradient, number of bumpers, like this. So in this parameter can change the energy consumption between the 2 points. So that has been written down here. So this is our C++ output program. So you can see that here the source node is, starting node is 1 written down here. Here in the left hand side, this is the original Dijkstra algorithm, which is calculating from the node 1 to node 6. Okay, so that is the shortest distance, and the path has been written down here 1, 3, 4, 6. This is the node visited while solving the original classical Dijkstra algorithm and calculate the distance between these 2 points. But in the right hand side, you are seeing that we are also calculating the minimum energy consumption between the node 1 and node 6, but you can see that the path is not same as the shortest distance path. That means if we use the original Dijkstra, whenever we are trying to implement a new method for calculating the minimum energy consumption, that path is 1, 2, 4, 6. So that two path is different. So we will not look into the shortest path distance, rather, as the energy is valuable nowadays. So we will look into the path where the energy consumption is minimum. So our selected path will be 1, 2, 4, 6. Okay. So that is our C++ output program that we have implemented. Next, this is the path. As I have mentioned, the shortest distance path is 1346. So you can see here 1346 has been marked as red. Okay, red color. So that color is the shortest distance path. You can see 255, that is the 12 kilometer. But the node visited it 1, 3, 4, and 6. But whenever we are trying to calculate the shortest energy calculation path, so that path is different from this path. So 1, 2, 4, 6. So that is our aim. So we will try to calculate a section of our road and try to get the model of this like this, a graph structure model connecting the different point, and we'll try to calculate the minimum energy consumption. And it has been found that in the many cases, almost many cases, the shortest path is not the energy efficient path. So here we have also seen that the shortest path is 1346, but the energy efficient path is in the green color, that is 1246. So that is our work. So we have also run the algorithm between the other two nodes, that is between the node 2 and node 5. Here we have run the program between the node 1 and node 6. Distance is 12. Okay, but whenever the energy is 18, you can see the difference. And whenever we try to run this program, due to the minimum energy consumption path, that means minimum energy is 12, but the distance is higher. So here we not choose the first one result, we choose the second one result, because energy is less here, but the distance is higher. Okay, and also we run the program between the node 2 and node 5, and you can find the path is different. And if we run the program between the 2 and 5, the path is 2, 3, 4, 5, and the distance is 9. Okay, but the energy consumption is 23. You can see the high energy consumption, though the distance is less. But if we run the program again between the node 2 and node 5 and calculate the distance, so 2, 4, 5 is the path, is the distance is 23 kilometers, maybe higher, but the energy consumption is 10. Due to the different root parameter that I have already mentioned, the different root parameter is actually affecting the energy consumption. That means the shortest route not only means the efficient energy consumption path. So that we are trying to implement here. We have seen, we have actually shown here the two results, and you can calculate between the any 2 point in the graph, between the any 2 point, node 2, node 5 I have calculated. You can calculate node 2, node 4, node 6, anywhere. You just put the program in the programming, that the starting node and the destination node, and the program will gives you the calculation result, final result. And this is our calculation. We have not looked into the efficient shortest path distance. We only look into the efficient energy management path distance. That means the shortest energy, lowest energy distance path. That is, we think that the energy is the most vital in today's, because it is the most costly thing today, because oil is actually very much costly nowadays, or the other energy alternative. So that's why we have implemented this shortest or the lowest energy consumption path. Now, as you can see from this result, that this is a optimized, this is a constant here. That means distance is here 12, energy is 18, here distance is 14, energy is 12. Now in the coming future, we will try to implement this paper further by applying some multi-objective evaluation algorithm, so that we can select which path is to be selected from the GA algorithm or other algorithm, so that we can not only look into the one parameter. Here we will look onto the one parameter, that means for the energy consumption point of view. But if we look into the multi-objective parameter, that means we want to optimize the kilometer distance, also energy distance, then we must take the help of evolutionary algorithm, so that multi-objective evolutionary algorithm, so that we can select the proper path considering the energy as well as the distance. Here we will only considering the single objective, that is for the calculation of the lowest energy path. So that's all about our work, and thank you. Hello, sir.
Hello.
Yes, sir.
Am I audible? No?
Yes, yes.
Okay. I have a small question. Just go to second slide of your proposed method.
Sorry, sir.
Second slide of your proposed method.
Okay, okay.
The next slide. Previous. Next. So the total average energy consumption is integration of P total into dt. So what is the expected lower and upper limit of P total?
We are trying to calculate between the time interval, energy consumption in terms of the time interval. That means the dt, time energy consumption.
So what is the lower and upper limit of that integral?
Lower and upper bound, that means we have first set the velocity. That means that we have here the set the velocity at 110, 80 to 110 velocity, and the time duration you can set anywhere from the program. We have all these put this data into the program, C++ program, and from the text file we get the data. But from the you can asking this.
No, but physically the limit should be in time, not velocity.
Integration we have performed between the 0 to 60-second time interval.
So you are telling velocity, that is not correct. It is from time. And whatever my second question that you already mentioned, that without least path and we cannot conclude least energy only, that you already mentioned. Okay. Sir, for me it's okay. If you have any question, please ask.
No, sir. It's okay. You cover all of the points. Please call the next.
Okay, then you stop sharing and we will call the next